Hello, welcome back. We are continuing our deep dive into deep neural networks. So far we have started to explore some regularization techniques which are specific to deep neural networks. So we started in our previous video with dropout, which is a specific type of layer that we have seen during training time randomly deactivates some neurons. Uh, we've seen that it's a very effective technique, and it's particularly efficient for fully connected layers. So now we'll be addressing a different type of deep regularization technique, which is called the Batchnorm, batch normalization, and which is one of the elements that have revolutionized the training of deep neural networks. So ever since Batchnorm occurred, training of neural networks has become a lot more smoother, faster, and more reliable and more predictable, with less instabilities and without the hassle of having to restart with different random seeds until the network trains properly. So we'll discover in this video we'll discover what is Batchnorm and what it tries to solve, what are the strong points, and what are the drawbacks of this technique. So just to begin, so we saw previously that to maintain, in order to that maintaining proper statistics of the activations and of the derivatives is a critical issue to allow to train deep architectures. So we have seen, for instance, in the sigmoid, that the derivative was key there to find the weak spot, and also the statistics of the activations were also key in order to set the data into the places where the sigmoid was most active with the steepest descent, and where it has the biggest slope. So in general, this problem in most of the cases is addressed by crafting smarter weight initialization techniques that take into account the activation function that will be used, the depth of the network where it will be, the number of layers, the number of weights of filters from the previous layer, also the number of outputs for the layer after, and so forth. So there's a lot of work done into this area, and it's an area with still that has received quite a significant interest, I would say. And another way of addressing this is by explicitly forcing the activation statistics during the forward pass to follow a certain range of values, and we do that by renormalizing them. So this is the case for batch norm. So batch normalization was actually the first method to introduce this idea. So it's a very nice paper by Yofe and Segedi in 2015, and we'll discover actually how does it do that. So I will start first with a note from the original paper with the motivation of the authors into this problem. So what they say is that training deep neural networks is complicated by the fact that the distribution of each layer's input changes during training as the parameters of the previous layers change. This slows down the training by requiring lower learning rates and care for parameter initialization. So when we look at an architecture, we can see actually what they mean. So during training, so I take here, well, explicitly a simple network, but we have deep neural networks to work with. So imagine that you have several hundreds of mini batches that go along this neural network. So you have a forward and a backward. So each time we have different images here, which act, which trigger along with the weight some certain ranges of activations that eventually lead to other ranges of activations when interacting with the weight sphere, and so on. So we might think that it's quite, by the way that these networks are constructed and everything, it's actually a matrix multiplication inside of the network. All these sensible changes in the input might actually lead to bigger drifts in the output. So if this happens for each image and for each mini batch, we can easily understand why optimization can be this tricky, because the statistics are evolving all the time with the input images, but also with as the weights of the networks of each layer change during optimization. So while I'm putting it again visually for a 3-layer MLP that we have seen before. So again, everything that's happening here is a sequence of matrix multiplications plus some additions of biases that we have omitted here, but it's still a lot of chain multiplications. So if something goes wrong in the beginning, we can see that towards the end of the network, there will be a huge, can be a potentially huge drift between what we were expecting to happen, what's happening. And so here actually you can see this as this is also due to the ReLU. So we see that with ReLU, the activation functions, we solved to some extent the vanishing gradient, but now since the input is no longer squashed, as we were doing with the sigmoid and the 10H, there's some more room for the statistics of for this drift to go on, because there's nothing to bound the activations for the second layer. If you remember, ReLU is the maximum between 0 and the input. So we keep the input unchanged if it's positive. So there's no squashing anymore to stabilize the activations. So batch normalization, since this drift can happen at any point in the network, batch normalization can be done anywhere in the deep network, and it forces the activations first order and second order moments, so that the following layers do not need to adapt to this drift at all time. So we will see. Well, I'll take the pseudocode from the paper that shows us how actually Batchnorm normalizes these activations in each mini batch. So here, this is a screenshot from the original paper. So at input, we have the values x of a mini batch. So x here are feature maps, and the batch normalization layer has 2 parameters, gamma and beta, to learn. At the output, we'll have the batch normalized layers, batch normalized activation, y, which are the output of the batch processing BN function, batch normalization function, depending on gamma and beta, and processing input xi. So what we first do in Batchnorm, we compute the mini batch mean. So for each, so we can see here M is the size of the mini batch. So we practically, for each feature map, we take the same feature map across all the samples in the mini batch, take all the pixel values, and compute the mean. For the second feature map, we do the same. So we'll have as many means as feature maps we have in that particular layer. We proceed similarly to compute the variance across the mini batch for each channel individually. And then what we do, we will use these statistics to compute some x hat that are just which is the normalized version of the input x. So we subtract mu b, the mean, from x, and we divide by the square root of the standard of the variance. Sorry. So this is our normalization. But as we remember, we have 2 parameters, gamma and beta. So far we have just squashed the values between -1 and 1. And what we do now, we have 2 learnable parameters, gamma and beta, which are doing a scaling and a shifting of our activations. So you might wonder why doing this even further, since we already have normalized this. So this is actually to enable and to learn more expressivity in our representation, right? So we want to reproduce whatever function we have at the output of these activations, and even if we are wrong or we have some instabilities in these statistics, the gamma and beta will allow us to move the activations in a more convenient regime for the subsequent layer, right? Because these gamma and beta are trained with so receive by gradient descent and backpropagation. So they receive gradient information from the loss. So in a nutshell, that's it. Right? It's on paper it's quite simple. If you take it on PyTorch, it's again quite simple. However, this technique has a lot of impact, so it speeds up and stabilizes training significantly. But well, it has some different implications on the optimization, and there's actually an entire literature nowadays studying the impact of Batchnorm on optimization. Because here, what might not be visible here is that because we are computing statistics on the mini batch and we then scale and shift them. Practically during the back propagation, we have again to go all the way through each of these parts to transmit the gradient descent. So it enforces an interaction. So beyond this normalization, it enforces also an interaction between the various outputs and the images that we have in the mini batch. So it kind of ties them together and optimizes together, and it considers this their interaction, if you want. So during training, this is what happens. So we shift and rescale the activations based according to the mean and the variance that we estimate on the mini batch. But as we need to pay attention that as we have seen for dropout, this type of layer behaves differently during training and testing. So we have seen that at training we normalize by using the statistics from the mini batch. But at this time, we might have an arbitrary number of size of mini batch, right? So we might have as in train time, we have I don't know, something like 64, but we can also have mini batches of size 1, right? If we're in we put our network on a device and processes images on the fly, we will have always one image process. So in this case, we have to find that there's a mechanism to make sure that the statistics are robust and we always normalize by the same amount, because otherwise you can imagine the statistics from a mini batch of size 42 might be different from the one from size 1. So what we do at test time, we use the average and standard deviation that we have computed across the whole data set during training. This actually shows also one of the major inconveniences, drawbacks of Batchnorm, is that in order to work properly, we need large mini batches to compute robust statistics for these mini batch. So in general, well, you should have at least 1632 images in a mini batch to have this work, at least for image classification. We'll go a bit into more detail into how this actually impact and what other solutions could be for that. Moving on to the PyTorch implementation. So like dropout, we implement Batchnorm as a separate module that processes the input components individually. So well, depending on the type of data that we have Torch Batchnorm 1D, Batchnorm 2D for convolutions, and Batchnorm for 3D convolutions. And Batchnorm 1D is for fully connected layers. So just to give you an idea on the dimensions and what's happening inside there. So I will just define here a random feature map, right? So it's a tensor of that mimics a mini batch of size 16 with 100 feature maps of spatial dimensions 7 and 7. So we will define a Batchnorm layer here that will correspond to that, and as you can see here, it's not related to the size of the mini batch, but it's actually related to the size to the number of channels, right? So you have as many parameters as channels I have in my input tensor. And what I do here, I just pass my my tensor through the Batchnorm layer and obtain an output feature map Y, which should be the normalized feature map. So first, let's see that well, I have my input X has this size here, and we can see that the input Y has exactly the same size. So it doesn't affect whatsoever the size of the output. We can see is unchanged. Then at the level of the Batchnorm layer, we can see that we have a field which is called weight. So this is the gamma, the scaling factor, right? And we can see it has a size 100, which is the number of feature maps that I have in the input, and the same for the bias, which is the shifting parameter beta, which also has the size 100. And what's specific to Batchnorm is that these two fields, running mean and running variance. So these are actually the fields where we store the temporary, where we store on the fly the average, well, the mini batch statistics, the mean and the variance. right? So we computed all on the fly, and we updated with each mini batch. We have an exponential moving average, so we have a value that's historically the mean, and then we do a linear combination with the current value from the current mini batch, and we update it gradually, and it's slowly moving, following the actual the most recent statistics from our mini batch. And we can see again that the mean and the variance are also of size 100, meaning that we have one per feature map. So now going in to see how it impacts training and performance in practice. So here we have well, this inception is a popular neural network developed by Google. So here there's the variant without batch norm. So we can see here the accuracy with respect to the number of training steps. Right? So here we have 30 million steps in order to get to this performance. And we have here several batch norm baselines, and you can see that all of them are way faster than the variant without batch norm. So we get to the same performance or even better in significantly fewer steps. We're getting even better, as I said, better accuracy than before. And the big advantage of Batchnorm is that it enables large learning rates because the statistics are stable. So we can this actually it's the secret for why we reach this fast this performance. And to some extent, it reduces the impact of L2 regularization. Though there's several studies, one from my group as well, that studies the relationship between Batchnorm, L2 regularization, and weight decay. So there are some finer interconnections there. And also it reduces also the impact of dropout and other normalization techniques that were previously used, and that, well, at least local normalization was made obsolete by Batchnorm at that time. As I said, one of the major weaknesses of Batchnorm right now is that it requires large mini batches to be able to be properly trained. So multiple variants have stemmed from the literature in the past years to find a solution to improve that, right? To find a normalization technique that works as good as Batchnorm, but without having large mini batches. So here I'm showing some of the most popular normalization techniques out there. This is a nice visualization from this paper here. So you have to make a bit of a mind exercise right now. So if we have flattened the spatial dimensions as HV, so we made them in one-dimensional vector. We have here C is the number of feature maps, so it says the channels, right? The slices. So we have here one channel, here one channel, here one channel, and so forth. And N is the number of images in the mini batch, right? So we can see that Batchnorm normalizes on the same channel from the same mini batch, right? So we get the statistics from the same channel across the mini batch. There's another technique which is quite popular in transformers and in recurrent neural networks, which is called layer norm, where we normalize practically all the feature maps from the same sample, right? So we see here that I'm always on the same sample, and I just normalize the feature maps jointly for on a per image basis. Right? So I take if for an image, as we've seen before, I have 100 channels. I compute one mean per one mean that is used for normalizing all the activations from the 100 feature maps of that image. For the second image in my mini batch, I do identically. I normalize it by its own statistics. So this is called layer norm. A more efficient way, but well, a more different way of doing normalization is the so-called instance norm, where we just normalize each channel by its own statistics, per image. So on each image, on each channel, we do a normalization by its own statistics. Right, so this is also quite it was quite used to alleviate to mitigate the drawback of Batchnorm. But what's actually more popular towards this problem is what we call the group norm, which appeared not later after that, which is somewhere in between instance norm and layer norm. We do normalization by groups of by specific subgroups of channels. Right? So here I take 3 channels and I normalize them together. Here I might take other channels and normalize them together. Group norm is also one of the most efficient ones that provide the closest results to batch norm when using small mini batches. So this is still an ongoing area of research, and there's various other works going trying to improve the things here. Batchnorm supporters are also working on distributed training, so you can actually you can simulate having a bigger mini batch by using more GPUs. Right? So if you dispatch the training across several GPUs, you can have like 2 images or I don't know 16 images per GPU, and you can synchronize the statistics of the batch norm or compute them jointly across the GPU to have to mimic as you had a very big mini batch that is used for training. And actually, there's some, even in PyTorch, you have some functions that allow you to do that in distributed training. An interesting approach for improving things here is what's so-called the weight standardization, which advocates for a solution for micro batch mini training, where you have 1-2 images per GPU, as I said before. And this is typically the case for heavy computer vision applications, where you have big images or complex tasks. So which is the case for object detection, or where we have to detect several objects inside of an image. So you have to take different guesses on the different parts of the image. So you cannot afford large mini batches. Or semantic segmentation, where we input high resolution images and we have to output high resolution segmentation maps of the same resolution as the input. So this requires a lot of GPU memory, and again, we cannot afford having big mini batches. So the authors here in weight standardization propose a solution here. So you can see that differently from the previous methods where you were normalizing the activations, they normalize the weights. So this method can be used with both batch norm and group norm. So what they do, they normalize for every layer. They normalize the filter by its own statistics, exactly as we do in batch norm. You subtract the mean of the weights of the filter and divide by the standard deviation. And we do the same for the second filter, the same for the third, fourth, fifth, and sixth filter. We do the same filter or convolutional kernel. And empirically, we've seen that actually this works really well. So here we have a comparison on red on ImageNet, so an ImageNet accuracy. So here we have the performance of group norm, which is trained with mini batch of size 1, batch norm with mini batches with large mini batches, and here we have a group norm plus weight standardization with mini batch of size 1 that outperforms batch norm with a bigger, which uses a bigger mini batch. So we can see this generalizing between on ResNet ResNet 50 and ResNet 101. And here on the right side, right hand side on blue, we have results on object detection on COCO. So here again we have a very complex network. Here, unfortunately, batch norm is used. Well, we cannot afford to have big mini batches. So it's trained with also with regular mini batches. So because of hardware constraints. So here we can see that group norm shines, but also when you couple it with weight standardization, we can see that the results are clearly better. So there's PyTorch code for this approach, and we've seen in the past year there's some ideas sparkling out from this approach. There's even a paper right now that advocates proposes an approach that actually doesn't need at all batch norm in ResNet, but we'll see that in the next video. So we've talked about batch normalization in this small video, and the various variants that are of it that we can encounter. We've seen the advantages of batch norm, which is stable training with large training rates, but also the drawbacks, which are related usually to the dependence on large mini batches. So I'll see you in the next video for our final video of the day on residual networks. Thank you and see you soon.